Come on. Okay. So for those of you who just got here a little while ago, we've been talking about one of the homework problems, lesson 6, number 1. It's a problem that has its issues. First of all, the answer in the back of a book is completely wrong. Appears to be for a different problem. And aside from that, simply working out the problem correctly is it's just really, really long and unduly tedious, I would say. For me personally, the most interesting part of a problem, what I would be scrutinizing most closely, like when grading it, is, are you transforming the boundary conditions correctly? And then after that, really the solution of a problem from there that deals with concepts from other lessons that you're already getting homework problems on. Now, if it were earlier, like if this had been a situation where, because I mean I've only just started getting questions on. I think I got the first questions on it like a few days ago. If it had been earlier and like y'all hadn't not started working on it yet, I actually would have changed the problem and X'd out the part about solving it, like just transform a boundary conditions and then we'll call it good. But I know that some of you have been working on solving it, and I don't want that to go to waste either. So what I'm going to do, let's see, if I look at how many problems are in this assignment, there are 7 problems altogether. So when I grade, I grade everything out of 100, just for uniformity's sake. And when I was a student, if I was crazy about it, I'd get grades like 9.75 out of 10. So in this case, like I would make each problem worth 14 points and give 2 points for free. So so what I will do is I will only require the part about transforming the boundary conditions. But if you go ahead and solve a transform problem, as some of you have already been doing, then because it's such a pain, I will give up to 2 problems worth, i.e. 28 points extra for going the distance on that, as a testament to what a pain solving this problem is. So it's almost like if you want to go ahead and do that one fully, and if you feel you got it right, then that's 2 other problems you don't have to do in this set. All right, so you can get a maximum score of 128 on this set, because apparently the solutions manual actually solves a different problem, and one that does work out somewhat nicer than what you see here. I mean, you're gonna go ahead and do it. It does give you good practice with certain things, but you're getting practice anyway. So, I think someone's about to ask a question. Walker, do you have a question?
Yeah. Do we still need to find the solution for 2? Or
wait,
I guess it says, what will the solution to this problem look like for different values of time? Does the solution agree with your intuition? It makes me feel like I would need to find a solution to answer these, but
I didn't sign that one.
Oh, you didn't? I thought it was 1 and 2. My bad. Or was it 1 and 3?
1 and 3.
Yeah, I guess I haven't hit 3 yet. I was just on 1.
Ah, okay. Yeah.
But also banging my head on that second part, so that makes sense. I just probably won't do that part now. But yeah, okay, never mind then.
Okay. All right. Well, does anyone have any homework questions? I think we can take some time for that.
Going from number 4 to number 5, was number 5 as simple as just inserting the factor.
Okay.
Like I feel like in number 4, we found the sine series, and all we had to do was then insert the factor, the exponential time factor. Was number 5 that simple as well?
Okay. So what would happen is, okay, I'm gonna share screen so everybody can see what's going on with this one. Okay. Now, I want to make sure that I'm understanding you correctly. That well, what happens is with problem number 4. Okay. Well, after you find this Fourier sine series for 5x equals 1, and then that's what you need in this problem here. Now, this Fourier sine series of 1 is going to have infinitely many terms, and it will, so that's what's going to happen for your solution for number 4. Now, if you look at the boundary conditions here, the solution U is set to be 0 at the boundary points. So your solution is a linear combination of these functions, sine n pi x, that we've seen in certain examples. Now, in problem 5, your initial data is already a linear combination of functions of that form, sine n pi x, for n equals 2, 4, and 6. So what happens in this case is, yes, the coefficients, if your initial data is a linear combination of basically your eigenfunctions, the solutions of your x ODE, then whatever coefficients you have for those values of n, like n equals 2, 4, and 6 in this case, will carry over to the solution. So when you're fortunate enough to get initial data of this form, writing down the solution of the initial boundary value problem is very quick. And Dale, I'm not sure if that's what you were actually asking about or something else. You're muted.
I was worried that I'd made it too easy.
Oh.
But it sounds like I didn't have anything to worry about.
Right. Yeah, you don't. So yes, it is quite easy in these cases. And this is something that I'll talk about when we get closer to time for the first test, because I do have some practice problems that I'm going to go over as for a review, and that's when I'll talk more about this case, this scenario that comes up sometimes with separation of variables, where you can just go from 0 to solution a whole lot more rapidly than like what I've shown you in class, where I'm doing the general case. Okay. Are there any other questions? Or homework questions, rather? Okay. While I have a book up, since I graded homework 1s over weekend, there's and generally people did quite well. Actually, yeah, everybody did well. But there's one mistake that popped up enough times for me to notice that I want to make a general comment about it. Okay, need to find the right lesson, right problem. Okay. Yeah. This problem right here. So this is number. So lesson 3, number 4. The boundary conditions: one end is fixed at 50 degrees. The rest of the rod is immersed in a liquid solution of temperature 30 degrees. A number of you treated these boundary conditions as exactly the same. Like for this one, let's say if we call this x equals 0, and then say x equals L or x equals 1 for the other boundary condition, then it's perfectly fine to say like u of 0t is equal to 50. That's the kind of boundary condition you have for this case. This other situation, rod is immersed in a liquid that's 30 degrees. That is not the same as fixing a temperature of a rod at that point. So, so you can't just say like, u of LT is equal to 30, and some of you did, unfortunately. There is a type of boundary condition that is literally for this case. That's one of the ones I discussed in class, and is also discussed in the section. Okay. It's type 2, so temperature of a surrounding medium specified. That's the kind of boundary condition you use for that case. And there were a number of you who did get that right. So be careful about that, distinguishing the two situations. That is something that will come up on the first test. So, so beware of that. And when I look at other mistakes that were made, okay. Well, I think that was definitely the one that popped up the most often. Okay. Now, when I grade these in Canvas, I after I mark your grade in the Canvas gradebook, then I also add a comment that indicates what problems you lost points on, how many points were lost, why. If you have any questions about that, just let me know, and I can give a more of an explanation of it. Yeah. Okay. Okay. For today, sort of a logical next step from what we have been doing, because suppose you have an initial boundary value problem, and it has non-homogeneous boundary conditions like we've just been talking about. So what you know how to do now is transform the problem so that the boundary conditions are homogeneous. So you have something equal to 0 in both cases, at both boundaries. But the PDE might turn out to be non-homogeneous, even if it was homogeneous before, especially if the boundary conditions depend on time. So now we're going to look at this case. How do you solve a initial boundary value problem where the PDE is non-homogeneous, while the boundary conditions are homogeneous? So how do we handle this case, and how can separation of variables help us? Because one of the limitations of separation of variables is that the PDE and the boundary condition should both be homogeneous. So what can we do in this case where this doesn't even apply? It turns out we still can use certain ideas from separation of variables, even if a PDE is not homogeneous. That's so. And the way we do that is, whereas in regular separation of variables, the ODEs that you separate the PDE into are homogeneous. Now we're going to have a situation where the ODE in time is going to be non-homogeneous. So then we can use standard approaches to solving non-homogeneous ODEs to help us in this case. So what I'm going to do is I'm going to talk about a very general problem just to give you a framework for how you solve these kind of problems, and then I'll work through an example. So I just want to warn you up front that when I'm doing this general case, it's going to be difficult to digest. That's because there's a lot of notation involved. And what I'm hoping is that when you see the example, then you'll see that it's not as excruciating as it seems at first. But I guess I'll have to let you be the judge of that. So the kind of problem we are solving is this kind of problem we've been working with. So here we have a very general diffusion equation where the coefficients p and q might depend on x. And generally in problems I give you, they'd be constant, but I want to cover this case also. And here we have the most general kinds of boundary conditions at x equals 0 and x equal L that are combinations of u and du dx. And then we have our initial condition. So this is about as general as we can get. Now, and here we have a PDE being non-homogeneous because we have this term f of xt. So for a heat equation, this could represent, for example, an external heat source. Now, what will help us solve this is the same PDE, but now homogeneous. So the f of xt is removed. So we can try, so this, because it's homogeneous, this we can go ahead and solve by separation of variables. Because we use the same boundary conditions, the boundary conditions are homogeneous. So what I could do is, if I substitute this into this PDE, so then I have something of this form, and then I could do like in separation of variables. I can isolate functions of t and x on different sides of the equation. So I'm just rearranging this. I have this part that depends on t, this part that depends only on x. So both of these must be constant. Therefore, it's equal to some constant, which I'll call minus lambda, or a minus is just a notational convenience. And here are my ODE. So this is just like separation of variables again. Well, it literally is separation of variables. It's just that this problem might be more difficult to solve, just because I have these variable coefficients p and q. What I'm showing you is that the principle behind separation of variables still applies in this case. Now, this kind of problem we've actually seen recently. It is called a Sturm-Liouville problem. And so when I discussed this earlier, it has eigenvalues, the values of lambda for which this PDE has a solution that satisfies the boundary conditions. When we have a value of lambda that works, I'll call it lambda n. The solution I call xn. What is also known is that they're orthogonal. So they satisfy this relationship that xn times xm, when integrated from 0 to L, will be 0 if m is not equal to n. So these, even though these solutions come from the homogeneous version of a PDE, they're still going to help us with the original non-homogeneous PDE. So what I can do is I can take any linear combination of these, and it will satisfy, so these will give me solutions of a PDE that also satisfy the boundary conditions. Okay. So now I'm going to go back to the original non-homogeneous PDE. What are we going to do with that? What I can do is I can express my solution, which I'm looking for, as a linear combination of these solutions to my Sturm-Liouville problem. And the same with the source term, f of xt. These are what are called Eigenfunction expansions, because I'm expanding u of xt and f of xt as linear combinations of my eigenfunctions that are solutions of my Sturm-Liouville problem. How do I get these coefficients? Well, that we've seen before too. So in general, they come from, like, to get the coefficients of un, I have a integral of u of xt times my eigenfunction, and I forgot a dx. Okay. Divided by the integral of each eigenfunction with its multiplied with itself. Now, this is actually what I've been doing in separation of variables all along, ever since the first day I started covering it. It's just that I've never phrased it in these general terms before, but this is something that always works for these kinds of problems. Like in the first examples, xn of x would be sine n pi x. So here I'd integrate sine n pi x squared from 0 to 1, and I get 1/2. And that led to a factor of 2 being in this formula for the coefficients. So suppose I take my PDE, my original PDE, and I multiply both sides of a PDE by xm and integrate from 0 to L. So then so that just gives me this. Now, what I can do is, if I take just this part right here and apply integration by parts twice, then I can actually change the roles of u and xm. So notice the difference between this integral and this one is that the roles of u and x of m are interchanged. And it's integration by parts twice applied to this term only that allows me to do that. Plus the fact that xm satisfies the boundary conditions. Because when you do integration by parts on this, you get terms evaluated at 0 and L. Why do those terms go away? Because xm satisfies the boundary conditions that are homogeneous. I don't want to take the time now to fully flesh this out. What I can do, like tonight or something, before I post these notes, I can add something in here to carry that out fully. Now, why do I do this? Because xm is a solution of my Sturm-Liouville problem. Now, this right here, if we keep in mind this formula right here, the numerator is exactly the same, except here I have a derivative with respect to time. And so what would happen is, if I take the derivative of this with respect to time, that's just going to give me du dt. So from this left side, I end up getting um prime of t, time derivative of this. Now, what about this right here? If I go back to my Sturm-Liouville problem, that is equal to lambda times x. I can replace all of this with lambda times x. So this whole thing condenses to minus lambda m, and then times um of t, that comes from here. And then if I compare this is exactly the numerator of this. So I get fm of t down here. I should mention that here we have these denominators, but this same denominator appears in every single one of these terms, so they cancel out. So from this equation, I end up with this ODE for each m. And the ODE is non-homogeneous. So from the original non-homogeneous PDE, I get a non-homogeneous ODE in time. So now I can try to solve this. But an ODE requires initial condition, and I have one from the initial condition of my original problem. So um of 0 comes from the same expansion applied to the initial data. So I need to expand that in my basis of eigenfunctions also. So now I just need to solve this. And once I do, I plug it back in here, and I'm done. That's the solution to my original problem. And this is a kind of ODE that you learn how to solve in your introductory ODE class using called an integrating factor. But I'll just give you the solution formula. It's this. In terms of the coefficients of f of xt and also the coefficients of your initial data. So now we can just use this solution formula. And now I can summarize the whole solution procedure. So here's a solution to my original non-homogeneous initial boundary value problem. For xn, I had to solve this ODE that comes from separation of variables for the homogeneous PDE, where you drop out, where you get rid of f. Has to satisfy the original boundary conditions. And then, to get these coefficients, u n of t, I use this solution formula. And for the missing pieces, an and fn, they come from here. So to solve the original problem, you compute you first get your eigenfunctions from your spatial ODE. Once you have them, compute these, plug them into here, plug this into here. Done. Now, that whole process is still a pain, but those are the steps. So really, if you're just trying to solve this problem, this is what you need to know. I mean, everything I did up to this point is just showing where it comes from, but this is a solution, outlines a solution procedure right here. And this is called the method of Eigenfunction expansions. Now, I will go into an example, but I want to see if anyone has any questions first. I probably fried 13 brains already, but okay. So here's the example, and hopefully this will define it a little bit. Because imagine right now the fangs are pretty big and scary. Oh, wait. Let me go onto a new page. So here's a problem to solve. This is the kind of problem that's more typical of what you see like in a homework or a test. So here's our non-homogeneous PDE that has this non-homogeneous term, or this is our f of xt. Homogeneous boundary conditions. And then here's the initial data. So first, you have to perform separation of variables on the homogeneous version of a PDE. So f of xt drops out. So then you do separation of variables like you've been doing, and you get these ODEs. You just solve the spatial one now. So this one you don't need to deal with because you're going to be solving a non-homogeneous one later anyway. Here are the boundary conditions. At x equals 0, x equals 1. And we've actually seen this one before. These are the solutions, sine n pi x, where n is a positive integer. You also need the values of lambda that work for these solutions, n pi quantity squared. So these give us the form of the solution of our original problem. So what I need to do now is do all my eigenfunction expansion. So my solution will have this form with sine n pi x filled in. Here, my initial data is expanded in its basis of eigenfunctions. And my source term is also expanded. Now, this gets to what we were talking about for homework, problem, oh, God. Problem 5, lesson 5. That in this particular case, the coefficients an and fn are particularly easy to get because the given source term and initial data are already linear combinations of these eigenfunctions. So what we get is a1 is equal to 1, because that will give you sine pi x, and then all other a's will be 0. Similarly for f of x, when n equals 3, we have f3 is equal to 1, and all other f's will be equal to 0. So now that I have these coefficients, I can describe the non-homogeneous ODEs I'm going to solve. So here's my solution formula, where I filled in the lambdas, n pi quantity squared, and we also have the alpha squared from the PDE that goes in here. I just need to fill in the a's and the f's. Now, the only time an a or an f is non-zero is when n equals 1 for a1, and then n equals 3 for f3. So what does that give me? That the only interesting cases are where n is equal to 1 or 3. So when n is equal to 1, f1 is 0, so I won't have this part at all. I only have this. So I fill in a1, which is equal to 1. So that is my coefficient for that term, or n equal 1. And then when n is equal to 3, I have this, but a3 is 0, so I'm not going to have this part. f3 is equal to 1, so I will have something here. So this integral needs to be worked out. So this term goes away. I actually carry out the integration. Notice the integration is with respect to s. So I could actually write this as I could break it up into two exponentials, this one and this one. The one with t is a constant, can be pulled out of the integral. This is what we actually integrate, and that's why we're dividing by 3 pi alpha quantity squared. And this is a definite integral, so I got to plug in the limits. Here, f3 is equal to 1. That's why it disappeared. So now I plug in the limits, and this is what I get. So these are the kind of terms that often pop up with non-homogeneous initial boundary value problems. So now I have u1 and I have u3. What about all other n? Well, for all other n, an is 0 and fn is 0. Therefore, the whole thing is 0. So that's why un of t is 0 for all n other than 1 and 3. So now I can take the two non-zero ones that I have and write down a solution of my original problem. So this is the term from n equals 1 multiplied by sine pi x. And here's a coefficient for n equal 3 that came from here times sine 3 pi x. And that's it. You're done. Now, what's interesting is, suppose you let t go to infinity. any decaying exponentials will go away. Like this whole term would go away. And then this part will also go away. So, so let's see, go infinity. This is the only part that remains. And actually, to clarify the formatting here, I'm going to put parentheses around these. All right. So that's how this works. That for your initial data and your source term, you work out these expansions. Now, in this case, they happen to work out nicely. Otherwise, you would be evaluating some integrals. So then, for whatever an and fn you get, you just work out what the solution formula is, and depending on the particulars of your problem, you may have certain terms not present, or you may have certain un of t just being 0 if an and fn are both 0. Whatever coefficients you do get, you put them in your you put them in here, and that is your solution. Okay. Questions about what happened in this example? I knew it. I fried everybody's brain. Well, half of you were already there from last class period, but still. You can bet there will be a problem like this in the first test. Well, I will say it is when I do compose the tests, it's very easy to take a problem like this and make it more of an exercise in Cal 2 than PDEs, depending on, because they all involve some integrals, and it is not my aim to make sure that your Cal 2 skills are intact. But whatever you know about these techniques, such as separation of variables and eigenfunction expansions. All right. Or does anyone have any further homework questions? Any questions at all? Or you're all like, I'm toast. I'm sensing some agreement there. Of course, those of you who are my research students, I can say, well, just you wait. But okay. All right. Well, I've probably inflicted enough mental anguish for one day. Oh, okay. Oh, Chelsea, I see your hand up.
Yes. So I noticed obviously sometimes the solutions are wrong, but when I was checking, I noticed that the alpha in the exponent of E wasn't included in the book solution, but I had it in my solution, and I didn't know if I was missing something, like if alpha was equal to 1.
Which problem?
I think it was on 4 and 5.
Oh, okay. Oh, from lesson
Sorry,
5.
from homework 2, lesson 5.
Okay. Let's see if I take a look at that. Whoops. Lesson 5. Well, if it is the sort of thing, it certainly can happen. Okay. Oh. Yeah, in problem 4 it says ut equals uxx, so alpha is indeed 1.
Okay.
Yeah.
Thank you.
But I appreciate you being more general anyway. Okay. But yeah, I'm already aware of, based on the problems that you've been doing so far, at least one mistake, and I believe there were a handful from when I taught this class last. Unfortunately, I didn't remember what they were, but we'll encounter them. All right. Last chance for any questions. Okay, then I will stop recording now. And hope your brains are intact for Wednesday.